Look around and you'll see a world running on lithium-ion, from the drone in the sky and the laptop on your desk to the electric vehicle in your driveway and the massive storage facilities supporting the power grid. We have been relying on the exact same chemical foundation since Sony put the very first commercial lithium-ion battery inside a camcorder back in 1991. Inside every one of those batteries is a basic setup: an anode on one side, a cathode on the other, and a liquid electrolyte bridging the gap. That liquid is the highway, allowing lithium ions to freely shuttle back and forth to store and release energy. But that liquid highway has a severe physical flaw. It is highly volatile. If the battery gets punctured or overheats, that liquid solvent acts as a readily available fuel source. Heat isn't the only threat. Every time you charge and discharge the battery, microscopic jagged metal spikes called dendrites grow off the anode. Over time, these spikes reach far enough to pierce the internal separator meant to keep the Q sides apart. When that barrier breaks, you get a short circuit. The electricity has a direct path to discharge all its energy at once, triggering thermal runaway. For over 3 decades, we have built our portable society on top of a chemical mixture that inherently wants to catch fire. To safely power the next generation of transport and infrastructure, we have to swap out that liquid foundation. The theoretical answer is the solid-state battery. Instead of a volatile liquid pool, this design replaces the core with a rigid, solid block of ceramic or polymer. With a solid barrier in place, those metal dendrites hit a literal wall. They cannot physically grow through the dense ceramic, eliminating the internal short-circuit fire risk. Once you remove the fire risk, you can change the chemistry. Manufacturers can pack the anode with pure lithium metal, effectively doubling the amount of energy you can store in the exact same physical footprint. This is why major automakers have spent the last decade promising that solid-state vehicles are just around the corner. We expected them by 2020. Then the target moved to 2025. Now we are hearing 2028. Billions of dollars have poured into this research, but turning a Nobel-winning theory into a mass-produced product means crossing the gap between perfect laboratory physics and the messy reality of global manufacturing. Down at the atomic scale, liquid electrolytes have a massive advantage. Fluids effortlessly flow over rough surfaces, expanding to fill every microscopic valley and groove to maintain perfect contact with the electrodes. Solid ceramics do not flow. When you press 2 rigid, uneven surfaces together, their jagged edges clash, leaving dark, empty gaps where the materials fail to touch. This is compounded by a phenomenon known as battery breathing. As lithium ions move back and forth during a charge cycle, the internal materials physically expand and contract. As the battery breathes, those solid layers physically pull apart from one another. The microscopic gaps widen, creating dead zones where the ions become trapped. Without contact, the flow of electricity stops completely. To force these stubborn materials to maintain contact, engineers have to clamp the cells together under massive external physical pressure, squeezing the battery from the outside just to keep the internal chemistry working. Building heavy, hydraulic-level pressure clamps into the floor of an electric vehicle ruins the weight and flexibility requirements for consumer cars. It turns a simple energy storage problem into a structural nightmare. Even if you solve the pressure problem, you run into an unexpected discovery regarding the core assumption of solid-state batteries, the idea that ceramic layers are physically too tough for any dendrite to pierce. Researchers at MIT recently discovered that the electrical current itself works against the material. The highly concentrated flow of lithium ions triggers a chemical reaction that actively degrades and dissolves the bonds of the ceramic lattice. Instead of acting like an impenetrable wall, the electrolyte becomes as fragile as glass. The growing dendrite easily shatters the brittle ceramic and punches right through, short-circuiting the battery anyway. And that is just what happens under a microscope. Scaling this fragile chemistry up to produce millions of battery cells introduces severe factory-level constraints. Pure lithium metal reacts violently with any moisture in the air. To manufacture these cells safely, companies have to build colossal indoor dry rooms, maintaining an artificial desert environment that demands huge amounts of continuous energy just to run the factory. Solid-state technology is trapped in a brutal two-front war. Engineers are fighting unpredictable chemical reactions at the atomic scale, while simultaneously wrestling with extreme environmental demands on the factory floor. Because pure solid-state perfection remains elusive, the battery industry is choosing pragmatism over purity. They are bridging the gap with hybrid, semi-solid designs. By injecting a tiny amount, roughly 5%, of liquid gel back into the solid structure, you give the battery just enough flexibility to fill those microscopic contact gaps without requiring extreme external pressure. This hybrid approach works so well that it is already leaving the laboratory. Automakers like MG and NIO are delivering real consumer electric vehicles today, powered by these exact semi-solid cells. It is a calculated compromise. It isn't the perfect liquid-free ideal we were promised a decade ago, but it proves that a partial solid-state architecture is highly functional and commercially viable right now. If we zoom out past individual electric cars, we face the massive infrastructure of the global power grid. To transition the world entirely to wind and solar power, we have to store energy when the sun shines and discharge it when the wind stops. That entire vision relies on overcoming this exact storage bottleneck. The final answer for grid-scale storage might be a pure solid-state battery, a pragmatic semi-solid hybrid, or even specialized liquid metal designs built strictly for utility plants. Ultimately, our transition to a renewable world depends on how well we can manage the flow of ions across these microscopic boundaries. The revolution will be forged one interface at a time.